Hello students, welcome to the EPG Pathshala. I am Ashok Goyal from the Department of Physics and Astrophysics, University of Delhi. Today we are going to discuss the solutions of differential equation, specifically second order differential equation, now with the specific boundary conditions from the paper Mathematical Physics. So student, what you are going to learn in this module is, for example, you will learn to obtain the solution of a Hermitian differential equation in relation to the boundary values imposed on it using the methods that we developed in the previous unit. We start by recalling that a complete solution of the differential equation involves specifying suitable boundary conditions. The number of such specifications depend upon the order of the differential equation. The most common equation encountered in physics, as I have mentioned several times in earlier modules also, are the second order differential equations for which two such specifications are needed for the complete solution, and the common boundary conditions that one has are of the Dirichlet type, in which one specifies the value of the function itself at the endpoints of the boundary, or of the Nyman type, wherein the value of the derivative of the function are specified at the endpoints. We can also have the mixed type boundary conditions, which is a combination of the Nyman and Dirichlet type of conditions and a specific combination of the function. So in this mixed type, some specific combination of the value of the function and its derivatives at the endpoints are specified. And finally, we have periodic boundary conditions, with which of course you are familiar from your earlier studies. For example, when in the theory of strings, vibrations of a string, or in quantum mechanics, when you consider a particle in a box, etc., one imposes the periodic boundary condition. The periodic boundary condition does not specify the value of the function or its derivative at any point, but it relates them at the endpoints. We will now illustrate with the help of examples how a complete solution of a differential equation is obtained when the boundary conditions are specified. We consider a simple second order differential equation d2yx by dx square plus lambda yx is equal to 0, where x lies in the domain from 0 to b, and the boundary conditions are simple of the Dirichlet type, that the value of the function at the boundaries is equal to 0, that y at a is equal to 0 and y evaluated at b is equal to 0. We have already proved earlier that lambdas are real, and hence the solution of this equation falls into three categories. That is, the lambda can be positive, negative, or 0. Let us first consider the case when lambda is negative. In this case, the solutions are exponential, and the general solution can be written as y of x is equal to a times integral of minus under root of minus lambda x plus b, another constant, e times plus under root of minus lambda x, where a and b are arbitrary constants and have to be determined from the boundary conditions. Now we have the boundary condition that y of 0 is equal to 0. So putting x is equal to 0, we have a plus b is equal to 0. We have also the second boundary condition that y at the other end of the boundary, which is at x is equal to b, is also 0, which would mean that when we substitute x is equal to b, then we get b sine hyperbolic of minus under root lambda times b is equal to 0. Now, since the sine hyperbolic function vanishes only if the argument vanishes, the constant b must vanish, since b is not equal to 0 for us. Thus, for lambda negative This equation with this boundary condition as specified has only a trivial solution, which is y of x equal to 0. Now let us consider the case where lambda is equal to 0. When lambda is equal to 0, the solution can be written in terms of two arbitrary constants c and d, and the solution is yx is equal to cx plus d. When we apply the boundary condition, x is equal to 0, y is 0, therefore this implies d is equal to 0, that x is equal to b, y is 0, therefore c times b is 0. Since b is not 0, therefore c is 0. So c is 0 and d is 0, therefore y is 0. Therefore, again we have the trivial solution that y of x is equal to 0. In the case when lambda is positive, the general solution y of x is e times sine of under root lambda x plus f times cosine of under root lambda x. This you can recognize as a solution of harmonic oscillator. Now applying the boundary condition that x is equal to 0, when x is equal to 0, sine is 0, therefore f cosine of 0 is 1. So this implies f is equal to y of 0, but y of 0 is equal to 0, therefore f is equal to 0, and e sine. Thus, for the non-trivial solution, therefore e sine under root lambda by b must be equal to 0, or else e is 0, in which case you have again the trivial solution. For the solution to be non-trivial, e is not equal to 0, therefore sine of under root lambda b must be equal to 0, which is possible if lambda b is equal to n pi, where n is an integer. Thus we have an infinite sequence of eigenvalues. Lambda is equal to pi square by b square, 4 pi square by b square, 9 pi square by b square, and so on and so forth. So in the case lambda going to positive, with the boundary condition as is specified above, a non-trivial solution exists and the eigenvalues are given in terms of square of integers. Corresponding eigenfunctions then are, for example, yx is equal to under root 2 by b sine pi x by b, under root 2 by b sine 2 pi x by b, root 2 by b sine m pi x by b, etc. The set of functions given above, namely y and x under root 2 by b sine n pi x by b, they form the basis of the Fourier sine series. And you know that in particular any function f of x satisfying the boundary condition f of 0 is f of b is equal to 0 can be expanded in terms of Fourier sine series, that f of x is equal to summation over n from 1 to infinity fn sine n pi x by b, where the coefficients f of n can be obtained very easily from the orthonormality of the circular functions, the sine and cosine functions, and fn, for example, here is equal to integral from 0 to b of dx fx sine n pi x by b. Now we take up another example which is very similar to the last problem. In fact, the equation is the same, but the boundary conditions are of a different type. So the problem is to solve the differential equation d2y by dx square plus lambda yx is equal to 0. Now with the boundary condition that the value of the function at the boundary point 0, that y of 0 is equal to 1, and the derivative of the function at the point x is equal to 1 is some fixed value minus y of 1. For lambda is equal to 0, the solution of the equation as before is y of x equal to ax plus b, where a and b are some arbitrary constants. When we impose the boundary condition that y of 0 is equal to 0, that means b is equal to 0, and the derivative dy by dx being equal to a, so dy by dx at x is equal to 1 is equal to a, so a is equal to minus y of 1. Hence, when we apply the boundary condition, a is equal to 0. Thus, there are no non-trivial solution in this case, and lambda is equal to 0 is not an eigenvalue. Lambda less than 0 is the interesting case where the solution indeed exists. When lambda is less than 0, the solution are yx is equal to a e to the power minus lambda x plus b e to the power minus lambda x. The boundary conditions then give us at x is equal to 0, y of 0 is equal to 0, therefore a plus b is equal to 0, and the derivative of the function is minus under root lambda a e to the power minus root lambda plus b e to the power minus of root lambda evaluated at x is equal to 1 is equal to a times e to the power plus under root minus lambda minus b times e to the power minus under root lambda. These equations lead to a multiplied by minus lambda under root multiplied by a to the power exponential of root minus lambda plus exponential of minus root minus lambda, which is equal to minus a times exponential of minus lambda minus exponential of minus lambda. Hence, when we apply the boundary condition, it is very easy to see that either a is equal to 0 and b is equal to 0, in which case we have the only trivial solution, is not of any interest, but there exists a possibility when exponential of under root minus lambda under root into 1 plus square root of minus lambda is equal to 1 minus square root of minus lambda multiplied by exponential of minus square root of minus lambda, in which case you can write that exponential of 2 times square root of minus lambda is equal to 1 minus square root of minus lambda divided by 1 plus square root of minus lambda, which is equal to 1 minus twice the square root of minus lambda divided by 1 plus square root of minus lambda. If square root of minus lambda is greater than 0, the left hand side is greater than 1, because if the square root of minus lambda is greater than 0, the right hand side is less than 1. Hence, the no solution exists for square root of minus lambda greater than 0. Similarly, if square root of minus lambda is less than 0, the left hand side lies between 0 to 1. The right hand side is greater than 1. Thus, the equation has non-trivial solution for lambda less than 0. At lambda greater than 0, the solution now can be written as y of x is equal to a cosine of root lambda x plus b sine root lambda x. Now we impose the boundary condition that x is equal to 0, y of 0 is equal to 0, so sine 0 is equal to 0, therefore a is equal to 0. And the second boundary condition of the derivatives says minus a root under root sine root lambda plus b times root lambda cosine root lambda is equal to minus a cosine root lambda minus b sine root lambda. So, from what we have discussed, we see that b times under root lambda cosine root lambda plus sine lambda under root lambda is equal to 0. So, either b is equal to 0, in which case we have a trivial solution because a is already 0, or tangent root lambda is equal to minus under root lambda. So, if we want a solution which is not a trivial solution, then we should have tangent of under root lambda is equal to minus under root of lambda. Thus, the equation which we consider, namely the equation 13.31, can be solved numerically, but from the well-known graph of tangent x versus x, it is clear that there are infinite number of roots of the equation lambda 1, lambda 2, lambda n. Because if you look at the graph of tangent x versus x, then there are infinite roots. Thus, in this case, we have an infinite sequence of eigenfunctions given by y and x is equal to b sine under root lambda n x. As before, the series of functions form a complete set in the domain x lying between 0 to 1. We now use a different equation to illustrate the solution. Consider the equation x square d2y by dx square plus 2x dy by dx minus lambda y is equal to 0, where x lies between 0 and 3, and we have the boundary condition that y at one point in the boundary, not at the function is defined or the value of the function is given at y1, which means at x equal to 1, and at the point 3, the y of 3 is equal to 0. The equation is a homogeneous equation. Equation can be solved by standard techniques with which you are familiar. Its initial equation reads s into s minus 1 plus 2s minus lambda is equal to 0. Remember that such an equation, which is a homogeneous equation and whose coefficients have no singularity, can be solved by series expansion method, and then you get initial equation, which in this case becomes s into s minus 1 plus 2s minus lambda is equal to 0. What we're interested here in this course is to apply the different boundary condition to obtain the solution. So we are more interested in looking at the boundary conditions and what it imposes on the solution. So the initial equation is a quadratic equation, so it has these two roots, one s1 and s2, given by minus half plus minus under root 1 plus 4 lambda by 2. Now there are various possibilities which we'll examine one by one. S1 and S2, first we consider the case where the roots are distinct and real. The solution of the equation then in this case is a times x to the power s1 plus b times x to the power s2. Now when we apply the boundary condition at x is equal to 1, then I have a plus b is equal to 0. And the second boundary condition gives me a into 3 times s1 minus 3 times s2 is equal to 0. Since s1 is not equal to s2, the last equation shows that a must be equal to 0. So when a is equal to 0, from a plus b is equal to 0, b is also 0. Thus, in this case, there is only a trivial solution if the boundary conditions are as specified above, namely the value of the function at the point 1 and 3 are 0. If the roots s1 and s2 are complex, which will happen when lambda is less than minus 1 by 4, in this case, the real part of the two roots are equal. So real part of s1 is equal to real part of s2 is equal to minus 1 half, where imaginary part of s1 is minus time the imaginary part of s2, which is equal to half under root of minus 1 minus 4 lambda, which we write as equal to p. So the solution in this case is yx is equal to, since the real part is minus half for both the roots, so y of x is x to the power minus half can be taken out, multiplied by a constant a into x to the power ip plus b x to the power minus ip, where p is the imaginary part, which is then x to the power minus half a times ip plus b x to the power minus half. We now apply the boundary condition at x is equal to 1. When we apply the boundary condition at x is equal to 1, we have a plus b is equal to 0. When we apply the boundary condition at x is equal to 3, we get 2a sine 3p is equal to 0. For a non-trivial solution, means a not equal to 0, b not equal to 0 to exist, we must have that sign of 3p is equal to 0, which means that n pi is equal to 3p. N pi must be equal to 3p. Substituting for p, which is under root of minus 1 minus 3 lambda by 2. So we have the non-trivial solution. If 3 by 2 into minus 1 minus 4 lambda is equal to n pi, where n is any integer, then is the eigenvalue condition, which gives me lambda is equal to lambda n is equal to minus n square pi square by 9 minus 1 by 4. So these are the eigenvalues, and for these eigenvalues, the solution exists. The eigenfunctions corresponding to the eigenvalues lambda n are yx is equal to 2a sine n pi by 3x. So the solution is yx is equal to In fact, 2 can be absorbed in A. So the solution is yx is equal to A sine n pi x by 3. Now in the case when the roots are equal, S1 is equal to S2 is equal to S. In that case, lambda is equal to minus 1 by quarter. Then the solution of the equation 13.33 is given by yx is equal to some constant A x to the power s plus b x to the power s log of x. Now the imposition of boundary condition on the solution leads to A is equal to 0 and 3 to the power s A plus 3b is equal to 0 and hence b is equal to 0. Thus in this case also there is only there is only a trivial solution. Let us summarize what we have learned. See what we did with the help of several examples. So we have learned to use the boundary condition to obtain the solution. So with the help of several examples, we illustrated the solution of differential equations, in particular of second order ordinary differential equation under specific boundary conditions by using the methods discussed in the previous unit. And of course, this is very useful practically in solving physics problems. Thank you.